Thank you for the introduction. So my name is Grant Pointon, and I'm happy to present this work, which is a collaboration between Vanderbilt University and the University of Utah. So, as many of you are likely aware, augmented reality devices and many applications are starting to make their impact on fields such as architecture, design, and medical imaging. And typically these applications try to help the users better understand complex layouts or even anatomical structures. Now in our lab, we believe that the use of such applications may depend on how users are perceiving the scale of AR objects or AR images. And by scale, I mean things like size, distance, and etc. Now some things that might influence someone's perception of scale could include the texture or the properties of the AR objects or the images. Another thing is the actual placement of the AR object, which is more relevant for the current study that I'll be talking about today. And why this is relevant is because many augmented reality objects or images can be placed in places that would otherwise in the real world not really be realistic or exist, such as just floating above the ground. So the main question that we asked in this study was essentially, can users of augmented reality devices perceive distances to AR objects or images if they are presented on the ground and off the ground accurately? So, as we just heard actually from the previous speaker, there's a lot of research on distance perception in both virtual reality and now there's been more so in some augmented reality. Generally in VR, there's this underestimation that we've seen. Recently with commodity level HMDs, this has been fairly reduced, and we also just learned some more about the nuances of this underestimation from the previous speaker. In augmented reality, there's been a few mixed results about whether or not there is underestimation. Some studies have found relatively accurate distance perception, whereas others have found fairly large underestimation, but there's not enough research right now to totally know, and we need to do more. So in this study, we're focusing on ground contact, which is an important cue for egocentric distance perception. And ground contact is essentially just the point at which the visual image of an object intersects the visual image of the ground plane. Some information helps specify ground contact for us, one of which is shadows and inner reflections of objects. Another is just binocular stereo vision. So, if both shadows, inner reflections, and binocular vision are absent, then it could cause a potential bias in how people perceive the distance to an object. As an example or illustration, on the left here, you can see that the left white panel looks farther than the panel on the right. However, the picture on the right is showing the actual setup of this illusion, which, as you can see, the left panel is actually about the same distance as the right panel. It is just above the ground. So without this information for us to know that it's actually above the ground, we perceive it as contacting with the ground but farther away. The same thing could be happening with AR objects that are presented off of the ground. And that's what we did in this study. So we focused on the Microsoft HoloLens 1. And we programmed all of our experiments with Unity. And we measured egocentric distance judgments with blind walking, which is a method that's been used in previous research and I'll describe soon. For our manipulations, we had the distance to target that we manipulated, the height of the actual targets, as well as if users were seeing the targets with binocular vision or monocular vision. We had a few challenges to overcome with stimuli creation because typically distance experiments are done in very sparse environments. That way it's a very isolated and controlled space. However, AR devices such as the HoloLens require three-dimensional objects in the actual environment for it to accurately map the space and to keep AR objects or images relatively stable. So, first, we did a pilot study before our actual experiment where we compared the amount of, as we call, drift that AR objects had in a populated space versus a sparse space. In the populated environment, there was things like railings, chairs, doors, and hallways for the HoloLens to map. And in the sparse space, it was essentially just an empty room. And what we found was that in the populated environment, the amount of drift was essentially negligible. And in the sparse environment, there was noticeable drift, but more importantly, some AR objects completely lost their mapping. So for the actual experiment that we ran, we came up with a bit of a compromise where we used just a single room and added only a few chairs to act as just stabilizers for the augmented reality system. We had three main hypotheses for this study. The first was that overall distances would just be underestimated to augmented reality targets. The second was that distances would be judged as farther for targets that were presented off of the ground versus on the ground. And the third hypothesis was that the off-ground targets would be judged as farther away with monocular viewing compared to binocular viewing. And furthermore, we did not expect there to be any effect of the viewing condition when the AR objects were presented on the ground. So, in our experiment, participants faced the opposite end of our lab space, and they used verbal commands in order to generate an augmented reality cube, which was just a white kind of marble textured cube. And they were allowed an unlimited amount of time to view the cube, and when they were ready, then they would use another command to make the cube disappear, in which case they would close their eyes and walk to where they think they saw the cube at. And when they stopped, we simply just measured that distance. So we got a sense of the apparent distance compared to the actual distance that people were walking. So for each subject, we presented the cubes at three different distances. That is 3 meters, 4.5 meters, and 6 meters. And each subject also did this task in binocular viewing and monocular viewing. And we can manipulate the viewing condition by having them wear an eye patch over their non-dominant eye. Each of the cube distances were also repeated 3 times each within both the binocular and monocular viewing conditions, which we blocked and counterbalanced across participants. We then varied the height of the cubes that they were presented at between the subjects. So it was either on the ground or 20 centimeters off of the ground. We ended up with 14 participants in the on-ground condition and in the off-ground condition. And for our analysis, we used a random intercept mixed model, which is essentially just comparable to our repeated measures ANOVA. And the model is displayed just below for anybody who's interested. We chose to do this because it allowed us to test only a few specific planned a priori comparisons that we were interested in. And we ran this model in R using the LME4 package. So here are the results. What you can see on the y-axis is the average distance that the participants walked for each potential condition. On the x-axis is where the cubes were placed. So this is in centimeters, so 3 meters, 4.5, and 6 meters. The colors of the lines indicate each condition. And you'll notice, too, that the blue and the purple represent the cubes that were presented on the ground, and the green and the red were representing the cubes that were presented off of the ground. The solid black line is indicating essentially what perfect distance judgment would indicate, or what it would be. So for our first hypothesis, where we predicted that the distances to AR targets would be underestimated, we did find support for this. In the on-ground cube condition, distances are underestimated by about 15%. And the off-ground cubes were also underestimated by about 7%. For our second hypothesis, again, we predicted that distances would be judged as farther for targets that were off the ground compared to on the ground. And we also found support for this through a main effect of cube height. And so what I've bolded here is the unstandardized estimate of the effect, or in other words, the difference that would be expected between the off-ground and on-ground cubes in centimeters. So in this case, the model would predict 33 or about 34 centimeter greater distance judgment for off-ground cubes compared to the on-ground cubes. And also the D there is just Cohen's D for anybody who's interested. For our last hypothesis, again, we predicted that off-ground targets would judge as farther away in the monocular condition compared to the binocular condition, which is exactly what we found. Specifically, the off-ground targets were judged as about 13 centimeters farther than the monocular condition, or than the cubes when viewed in the monocular condition. However, we also found an unexpected effect of the monocular viewing condition for the cubes that were presented on the ground. Specifically, cubes that were presented on the ground and viewed monocularly were seen as about 12 centimeters closer, in fact, compared to the on-ground cubes when viewed binocularly. So, to sum up, we have essentially found more evidence to suggest a general underestimation of augmented reality objects, even if they are displayed on the ground. And we also have revealed a few open questions related to the distance perception of on-ground targets in AR. We have a hunch that the effect of monocular viewing on on-ground targets could have been due to the fact that we use relatively high contrast stimuli, but we're investigating this right now, and so we're still not totally sure. And lastly, and most importantly, we found that off-ground targets were perceived as farther, which replicates previous work with the illusions and also some real-world study that shows that when ground contact or when objects that are presented above the ground are not accurately perceived as so, then they are perceived as farther away but on the ground. Additionally, we've established that there is an importance of binocular viewing for this effect. Specifically, binocular viewing may be important, particularly in the AR domain, for accurately perceiving the distances to AR objects or images that are presented off of the ground. And lastly, we are thinking about future work that investigates the shadows and potentially even inner reflections of AR objects and images. So I'd like to thank you all for your attention, my co-authors, and the Office of Naval Research, which funded this study, and is my mother, of course, so hi, Mom. And thank you.
Hello. I have a concern about the fact that the person walks. So every claim you do have this, I think, this passage of estimation at distance to the operation of estimating at distance and perform an operation. And this operation can have also, I can mean as a researcher, this passage, I would like to have more justification about how you can claim starting from this complex operation.
For the blind walking, you mean? Yes, so blind walking has been done in the real world many times, and it's actually been found that humans are fairly accurate at blind walking to targets even up to about 20 meters or so. So we've done this. This is how many other virtual reality experiments have also been done. So that's where the motivation came for our blind walking procedure.
Hi, I am Luciana Nedel from Federal University of Rio Grande do Sul in Brazil. Nice work.
Thank you.
My question is, what makes the cube that is off-ground different than the one that is on-ground? For example, for the user, what he's seeing as a background is the floor also, or perhaps the wall, I don't know.
If I understand your question, the only difference that they, well...
Yeah, perhaps I can clarify.
Yes, please.
It's because you are not using shadows. If you are using shadows, you can see that the off-ground cube is flying, and then you could change it could change your perception. As you are not using shadows, what makes the cube that is flying different than the one that it's on the ground?
I see. So it actually might not necessarily look that different than the cubes that are presented on the ground, but it's sort of this illusion that we're claiming, which they are just seeing it on the ground but farther away compared to the ones that are on the ground but shown at the same distance.
Okay, but in this way the user can just think that it's another cube on floor but farthest.
Yes, they could think that, but that's I guess, the idea behind the study.
Okay.
Is that we're sort of inducing this. It's similar to the illusion I brought up earlier.
And
where-
both have the same size?
Yes.
Uh-huh.
Yeah, all the cubes were presented with the same size. So yes, it would be similar to this idea. There's nothing that necessarily looks different between these two white panels when you're seeing it from this perspective, but if you were to get up closer or see it from different perspectives, then you would notice that there actually is a difference, which is just the height.
This was my question. In the first image, both are, the base of both are on the floor. The perception,
No.
the perception at least, the perception. In the second image, the one that is in the left, you
Yes.
can see that the background is it's not the floor, but it's the wall. Okay,
Sorry.
thank you.
We can talk after.
Okay.
Hi, I'm Frank, University of Hamburg. Thanks for your talk. Maybe a follow-up. So from understanding, the object appears to be further away, attached to the ground. This
Yes.
is your hypothesis, why people walk further. So my question would be, is the underestimation, I mean, they walk longer, but obviously they still have an underestimation. And does this correspond to the same underestimation that they would have if you would display the object further away on the ground?
Oh, yes. So let me show you. In the paper too, we actually predicted. We have a predicted distance of what would actually where would people potentially see the cubes that are presented off of the ground if they were seeing them as on the ground but further away. And so the amount of underestimation, I don't have the ratios here, but I believe it is about the same amount of underestimation for cubes that are presented on the ground, and also the predicted difference, the difference between the predicted distance and the cubes that were off the ground.
Okay, so if you would have allowed, for example, the user to make more movements to get some motion parallax and understanding that it's really hovering off the ground, there is not much research done probably in this area to estimate.
No, yes, not yet, but that is a good avenue for future research.
Yeah, well, the speaker one more time.
Thank you.